and welcome to our special on the 2021 Shaw Prize. Magnetars were only theoretical objects until two scientists confirmed their existence. Now magnetars tell us much about fundamental physics and have helped prove a number of theories, some proposed by Albert Einstein. Chryssa Kouveliotou and Victoria Kaspi are the co-winners of the 2021 Shaw Prize in Astronomy for their work on magnetars. It's the first time two women have been awarded the prize in a single category.
Chryssa Kouveliotou liked the night sky growing up in Greece. She knew she wanted to find out more, and getting a special gift from her father helped turn her towards a career in astronomy.
I just looked at the stars and I just figured something is hiding up there and we have to figure out what it is and maybe even go there. And basically that's what started me. And I should say I owe a lot to my father as well, because when I was a kid, let's say 10 years old or something, grammar school, basically he gave me a very beautiful cosmology book. In these days, cosmology was not as developed as we know today, but they had beautiful pictures, and they had also very nice pictures of the planets in our solar system. And I was taken completely from this book. So I kept reading it and didn't understand a lot, but it was actually beautiful. So that's the first interaction I had with astronomy.
Along the way, a high school teacher convinced her that physics would be an excellent career choice, even for a woman, which at the time wasn't what women studied. But become a physicist she did, and then an astrophysicist, after studying in Athens, Britain, and Germany. Her path led her here, George Washington University. The 43-acre campus sits in the heart of Washington, D.C. And it's where Chryssa Kouveliotou studies some of the most extreme objects that nature can produce in the universe. A neutron star is the remnant of a massive sun that has reached the end of its life, literally going out with a bang. What's left is a neutron star, a much smaller, much denser celestial carcass.
Neutron stars come in different varieties. Magnetars is one of the most extreme of them. They have properties that are not accessible on Earth. They have extreme densities, extreme gravity, and extreme magnetic fields.
Chryssa and her team confirmed the existence of magnetars in 1998, which had only been predicted in theory. But there were clues of their existence, repeating and persistent bursts of energy from a particular location in the night sky.
When we were looking at these repeating bursts, maybe we are actually discovering a new phenomenon. But all we had were the bursts. We knew the general direction in the sky of where this was coming, and therefore we could sometimes get the bursts, but we had to actually point a satellite towards that direction and get more information, like the persistent emission.
She wrote a proposal asking to use the Rossi X-ray Timing Explorer, a satellite that proved predictions in Einstein's theory of relativity, among many other valuable observations. It was approved, and with the data gathered, they were able to measure the spin of these objects, and with that, their magnetic fields. Very powerful magnetic fields.
It was 8 times 10 to the 14, 6 times 10 to the 14 for the other source. We looked at two sources. So the first paper was published about the existence of magnetars in 1998, if I remember correctly, and I was the first author because my team and I discovered that. And that was the first time that we actually had solid measurements, or I could say measurements of this magnetic field strength. So that started the magnetar family.
A lot of people, if you think about what are the most extreme objects out there, people often say like, oh, black holes, because they're so mysterious. But also magnetars, they're so extreme, they're extremely massive, but also extremely compact. And then they have these magnetic fields that you cannot really even dream of recreating here on Earth or in any kind of lab. And by just studying them, by observing them, we actually get to study physics under these very extreme conditions.
The magnetic field around Earth, the thing that protects us from the charged particles of the solar wind, is about 1,000 trillion times weaker than a field produced by the magnetar Chryssa found. Barely a fraction of a fraction.
What is the strength of this dipole field? And it turns out to be basically the largest that we've ever measured in the universe, and still to date.
We can understand better the theories and the models that have been developed here on Earth by observing properties of sources that have extreme values, and we cannot produce them here on Earth. In other words, we use them as probes of the extremes. And we're trying to understand how physics work in the extreme environments and how different they are from what we call normal here.
Chryssa first started looking for magnetars while she was working at NASA in Huntsville, Alabama. A job, she says, was always a dream of hers since her school days. She clarifies the popular notion that NASA just blasts rockets and astronauts into space, ignoring the fact that the agency does science too, lots of big science, such as in her field of high-energy astrophysics.
NASA has scientists, about 30% in the science centers, which is JPL and Goddard. Basically, and actually even other centers all of NASA centers have scientists, and all of NASA centers have a specialization in a particular direction.
Colleagues say she likes to build strong relationships with her co-researchers.
She built a family around research. All her colleagues are part of a family. Actually, all the young scientists part of the group here have been mentored and trained by her from the very beginning. So she has already been extremely careful of people. She knows the skills of all the researchers around her. She knows how to build a team. When there is a specific project, she knows where to get the skills, who she has to work with.
He says one of the advantages of working at NASA is that scientists get to use all the latest tech, which wasn't always the case, especially when Chryssa first started.
Chryssa has been working there at the beginning of her career. And I heard many stories about her going across the campus at Goddard, carrying tapes with data on them to analyze those data. So what were the technology 15, 20 years ago?
She and her team eventually used digital and network technology to analyze data. Chryssa spent 25 years in Huntsville before retiring in 2015. She joined the physics department at George Washington University. Chryssa is currently the chair of the department. Colleagues say she had definite research advantages being on the NASA team.
You're more directly involved in the development of new missions, new instrumentations, and so, which of course, can happen at the university as well, but there's a more direct link to the people actually building the missions, developing the missions, and then you as a scientist have a bigger chance of actually getting direct access to the data earlier because you're part of a mission team, for instance. So it's a little bit different than as a scientist, but as a scientist at a university.
At NASA, I did not have to teach, I did not have to prepare classes, I did not have to do anything else but research. So that was much more effective, much more productive.
NASA was also where Chryssa met her husband, Jan van Paradijs, one of the world's leading astrophysicists. He and Chryssa collaborated on many studies, co-writing 89 papers together. Passed away in 1999. During their working life together, they shared many ideas about their work.
Way too many And that's why I recommend that you don't marry exactly the same person in your work environment, because you can't get away from work. I mean, you come back home and you talk business again instead of talking everything else. But it was extremely useful in that sense, because we had students together. We were working on a lot of things together. We were very successful as a couple. And he was my soulmate. I mean, unfortunately, cancer took him.
Chryssa shares the 2021 Shaw Prize in Astronomy with Victoria Kaspi, the first time 2 women have won a Shaw Prize in a single category.
Hey, great. I mean, we love it. There's no way I would have expected it. It happened. I think it was about time to happen. The conditions were right. I'm just grateful to the committee for the nomination. But I am very exuberant with the fact that 2 women got the prize.
We'll meet co-winner Victoria Kaspi after the break. Victoria Kaspi has made a career looking for spherical objects, ones that you can't hold in your hands or pass to the kids on the basketball court.
I'm on.
The spheres she's after are a type of neutron star called magnetars, objects that lie millions of light years away from Earth. They're some of the most extreme objects in the sky. Observing unusual X-ray emitting pulsars, Kaspi confirmed they were actually another type of magnetar, establishing them as a distinct new group of objects. It was a slam dunk.
Finally.
They exhibit really unusual and dramatic, violent phenomenon like large X-ray bursts, soft gamma ray bursts, and now we even know they also emit huge radio bursts as well. And we know of a couple dozen of these in our galaxy, so they're quite rare objects. But we think they're basically an extreme member of the neutron star population.
She had just entered the field of astrophysics when there were new X-ray satellites being launched. They offered the chance to get in on a promising field, literally from the ground up. She was inspired to look at unusual X-ray sources after a lecture she attended at the California Institute of Technology.
They had all these weird X-ray properties and were a total mystery. People did not understand what they were, and that caught my attention. And from that lecture, I had some ideas about how to attack the problem, and that's what they turned out to be magnetars. And it was from hearing this lecture from outside my field and having known a little bit of X-ray astronomy, I realized, I can apply some of what I learned in my PhD, bring it from radio astronomy to X-ray astronomy, and I thought I'd give it a try, and I did, and it worked.
The significance of Vicky's work is that she solved a big mystery in astronomy, namely these objects known as magnetars. So for a while, people were making observations and just had no idea what these things were. And now we know that these are essentially neutron stars that are some of the most extreme objects that we know of. And basically, Vicky came along and figured out what these extreme objects were.
Growing up in Texas, Kaspi loved to solve puzzles when she was little and found that math was her favorite subject. And she was good at it. She set her sights on a career in some form of science.
At the same time, I was a huge Star Trek fan, and I really enjoyed thinking about the cosmos. I liked reading Isaac Asimov books about science fiction, things like that. And then really, I would have enjoyed doing almost any kind of of hard science, hard quantitative science. But I had the opportunity to do astronomy. I got a taste of it and I fell in love.
Kaspi has admired the work of women in science, including her co-winner, Chryssa Kouveliotou. But her admiration goes farther back.
I was very inspired by Marie Curie. I thought her life was fascinating. I thought she was an amazing person, tenacious and brilliant and hardworking and so accomplished. She was definitely a role model for me as a kid. Then I would say in university, my role models, you know, my PhD supervisors were wonderful role models, Joe Taylor and Dick Manchester. They were also very thoughtful scientists, very meticulous.
Kaspi continues her pursuit of high-energy astrophysical phenomena as the director of the McGill Space Institute at McGill University in Montreal, Canada. Now she is the mentor, advising the astronomers of tomorrow.
She cares a lot for her graduate students, and she cares a lot for the work that she does. And she wants her graduate students to be excited about what they do, and she wants everyone to be doing what they love and feeling just as passionate about their work as she feels about her work.
She hopes to pass on the things she learned from her own teachers. Be meticulous, systematic, trust your instincts, and if something goes wrong, stay cool.
My PhD supervisor in Princeton University, he was a very friendly person. He taught me skills of interacting with others. He was just a master at doing that, very inspiring in that way. And of course, he taught me a lot of science as well, about how to use, how to analyze pulsar timing data, different style of pulsar timing data. But overall, I think what I took away from them is love of science and you know, enthusiasm and how to share that enthusiasm with others.
One of her former students thinks Kaspi brings a great curiosity to astronomy, keeping her on the lookout for new stuff to discover.
One thing that I think makes her very special is that she always tries to push herself towards brand new science and astronomy work that comes out So it's like she won't get stuck working on the same thing over and over, but she'll like pursue new frontiers in science, and that's like what I think it's like very unique to her.
Kaspi's fresh new puzzle that she's trying to solve is the mystery of fast radio bursts, or FRBs, a radio pulse from an unknown source lasting milliseconds, first observed in 2007. The race to identify these phenomena has turned into a mad scramble to observe more of these mysterious events, which occur outside the boundary of our own galaxy, the Milky Way.
I think that fast radio bursts is one of the hottest topics in astronomy currently. I mean, you've got people all over North America, you've got people in Australia, you've got people in Europe, you've got people on every single continent working on these objects.
The commissioning of a telescope in British Columbia, Canada, revolutionized the field. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, is a collaborative project where Vicky is the principal investigator. Normally, radio astronomy can focus on one point in the night sky. But CHIME can reel in vast swathes of data, more data than in all the world's mobile telephone networks, 13 terabytes per second.
We populate the axis of the cylinders with hundreds of antennas, and then in a computer, in a supercomputer, we combine them and we can be sensitive to different positions on the sky all at the same time. So it's like having, in fact, we have 1,000 of these. It's like having 1,000 telescopes all operating at the same time, 24/7.
The number of bursts measured by the facility over time was exponential in scale. The new telescope detected over 2,000 fast radio bursts in just a few years from its launch in 2017. The field had exploded.
We're detecting lots of these things, and we see like these interesting structures. We call this the sad trombone effect. you see it starts, it's earliest at high frequency and then comes down. And that's not dispersion because we've corrected for dispersion here. This is something at the source, and we call it a sad trombone because it goes like wah, 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 like that. And we actually make that noise in public talks because it's so funny.
Like magnetars, FRBs could reveal much of what we do not know yet about the universe.
Maybe we can use fast radio bursts to detect dark matter. Or maybe we can use fast radio bursts to study the early universe. Or maybe we can use fast radio bursts to learn about these faraway galaxies that we don't already have a lot of information on. Or maybe we can learn a bit about our own galaxy using these fast radio bursts. Or maybe we can learn about the stuff that lies in between our galaxy and other galaxies. And so there's really this wide range of study for these objects.
Victoria Kaspi shares the 2021 Shaw Prize in Astronomy with Chryssa Kouveliotou. The first time two women have won the Shaw Prize in a single category.
I'm deeply honored. I'm delighted to have been given it with Chryssa, who is a formidable, brilliant scientist. I think there are many, many extremely capable and accomplished women who I feel confident will be getting Shaw Prizes going forward. So we might be the first, but I'm 100% sure we won't be the last.